I'd like to welcome two presenters to the virtual stage. The first is Trenton Thornock. Trenton is a founder of Wyoming Hyperscale White Box, the developers of the Aspen Mountain Hyperscale Data Center project, which encompasses 4 operating large-scale wind projects and 1 large-scale solar power project that together produce more than 500 megawatts of renewable energy. Secondly, I'd like to introduce Steve Jennings. Steve leads the ZincFive sales and marketing organization and brings 24 years of executive experience in technology companies serving the energy, clean tech, communications, computing, and semiconductor industries. Together, they will join forces to highlight the importance of building greener batteries into a sustainability plan for low-carbon data center operations. Without further ado, I'll hand over to Trenton.
Well, thanks, Alex, for that introduction. It's a pleasure to be here today with Steve Jennings, the Senior Vice President at ZincFive. It's been a great partner. And so I'll jump in with an introduction to Wyoming Hyperscale. So essentially what we're doing at the Aspen Mountain project is building what we call next generation hyperscale. And that means that most of the hyperscale that's been built to this point is air cooled. And for sustainability purposes and cost reduction purposes, we are moving to liquid cooling. So the challenge here is really twofold. On the one hand, we have data center chip temperatures that are going through 300 watts, where it becomes difficult to cool with air. We've got new chips that are coming out at 560 watts and higher. So that's the first part of this challenge. The second part is by 2025, cooling will consume 10% of the world's electricity, according to some. And that trajectory is unsustainable. So our idea is to look at these two challenges and face those down with existing patented and patent pending technologies. So some of the challenges that we see are easy to spot. They're in the press. There are issues around the amount of water that the data center industry consumes. We have sustainability issues. We have carbon reduction plans and goals. And we also want to make the industry more efficient and clean going forward. Some of the challenges that we see is that a lot of the ESG talk is just that. It's not really having any impact on climate change. We also think that it's unwise to continue to build large data center campuses in highly populated parts of the United States, such as Washington, D.C. Metro and Dallas-Fort Worth. We're addressing the high cost of air conditioning. And because of our location, we're not subject to any of the natural hazards that come to companies that are located near a coastline. One of the other things that we're trying to do is to positively benefit the community that we are constructing our facility in. We've been there for more than 6 generations, and this is very important to us. As I mentioned earlier, a large percentage of planned server chip production is going to require liquid cooling. So what we've seen is that we're currently blowing through the ASHRAE asset limitations around 300 watts, where it becomes virtually impossible to air cool these chips. And as I mentioned earlier, there are chips that are in the 500 to 600 watt range, and now we're seeing GPU chips that are between 800 and 1200 watts. So they're very hot, they're very fast and advanced, but it's getting more and more difficult to cool those. So our solution is to build in a little bit different place, and most people will say, well, Wyoming's too far away from population centers, but the fact is that our facility is located on existing splice points in the long haul fiber backbone, And so we are able to have ultra low latency connections to most of the metros in the United States. Some of those have already been provisioned. One of the other unique parts of our architecture is we've eliminated all the fans on the external part of our cooling system. So we have no adiabatic coolers, dry coolers, or cooling towers associated with our data center, and those all consume, at least with the exception of dry coolers, some amount, or in the sense of cooling towers, large amounts of water. So one of our main goals here is to become more sustainable by eliminating water consumption. And the solution that we came up with was to move to liquid. So one of our partners is Submer. We will have submerged dielectric fluid in our data center. It has some great attributes and is now being manufactured by Lubrizol, which is part of Berkshire Hathaway. So it has some fairly strong capital behind it. It has some great attributes in terms of how it protects the IT hardware, and it eliminates most of the issues that we see with OSHA, which is the Occupational Health and Safety Administration in the United States, with regards to hot and cold aisles. So instead of having very high velocity air blowing through our data center and some of that being very hot, we'll basically have a silent data center filled with liquid cooled ITE and basically just an ambient temperature with almost no air movement inside the data halls. Now, along with that, we've also selected ZincFive as the solution to lower our carbon footprint and make the UPS part of the data center more sustainable. And these are the three reasons that we selected ZincFive. The first one is to lower the carbon footprint of the overall data center. So we're using one-click life cycle assessment in order to track the amount of carbon that goes into the construction while we're building the data center. And part of that will be focused on the ZincFive solution. The next piece is safety and performance. You know, I have a strange background in terms of being a past user of lithium batteries, and also I've been the CFO of one of the largest zinc recyclers in the world. And so the nickel-zinc battery construction delivers a lot to us in terms of recyclability, which I think is going to be more and more important going forward in terms of lessening our impact on the climate. So what we end up with after all of this is a sustainable hyperscale architecture that actually ends up being less costly to build and operate than current air-cooled designs, which is a little bit counterintuitive. So by partnering with ZincFive, that also helps us decrease our carbon footprint, decrease our failure rates, and increase our uptime, which are all important things for data centers. And with that, I'll move to some of the other benefits that we get as kind of side benefits to the technology stack that we're working with. The first one is that we're dropping cooling OpEx by 95%. And again, it's projected by 2025 that could take up to 10% of the world's energy supply. So we think that it's very important to implement that now. We get about 10 times, it's actually more than that, more dense compute within the data center halls. Our CapEx goes down by half based on the savings of space. And the last two are only calculated on about 3 years of runtime, because those are the oldest deployments that we have in warranted ITE for liquid cooling. We think that the hardware lifespan and hardware failure rates will actually be better than what we're showing here once we run them for longer. Again, this architecture is drastically reducing our carbon footprint. This PUE 1.03 is the submer pod by itself. We expect a facility level PUE of about 1.08, which again is a step change from what we see in other places. We waste none of the water, so we consume no water in the compute operations, and we can recapture and reuse 99% of the heat that comes from compute operations. So this becomes a very sustainable approach to the data center industry, not only from an ESG perspective, but also a total cost of operations, a CapEx, and an operating expense perspective. These are some of the other side benefits that we get with our first phase, which is 30 megawatts. And you can see, just to put into context, the amount of resources that are going to be preserved and not used in the first place just by changing the architecture here. So with that, I'll turn this over to Steve Jennings with ZincFive.
Well, thank you, Trenton, for that overview of the very innovative Wyoming Hyperscale White Box facility. We're proud to be a partner in that facility. And what I'd like to do next is talk a little bit about the ZincFive contribution to the Wyoming Hyperscale White Box facility. First, just a little bit about ZincFive. We provide, or are the world leader in nickel-zinc batteries and power solutions based on those batteries. And we are focused on the mission-critical applications in the market and across multiple markets. And so that's why our products are real-world trusted across a variety of industries and infrastructures, including data centers. We call that the power of good chemistry. Let me talk a little bit about our batteries and how they compare to other batteries in the marketplace today. We talk about immediate power, and that term reflects on the fact that our batteries are very strong at short duration or immediate power, less than 1 hour type discharges. And that's very important in the data center space, where the typical runtime today in new data centers being designed with centralized battery backup is 5 minutes or less. And therefore, our batteries are very well suited to that sort of thing. There are other batteries being used in the data center today that are good at short duration and even long duration, as you see in the chart on the right, 1 to 6 hours or 6 hours or more. But the true application requirement within most data centers today is for immediate power. And that's our strength. If you want to think about it in more generic terms, immediate power is a sprint. In other words, high discharge rates, getting as much energy out of the battery in the shortest period of time possible, versus a marathon that an energy battery would be able to support, which is moderate to low discharge rates over longer periods of time. So when we build our batteries for immediate power applications, we're able to do that in a sustainable format that's good for business people and the planet. And we're going to dive a bit deeper on the sustainability contribution of these batteries to the data center. Let's talk about where we are with battery storage in the data centers today. Lead acid has been and remains the largest installed base of batteries in the data center today. However, a market migration was triggered by lithium a half dozen years or more ago. And since that time, lithium batteries have incurred significant market share in the data center marketplace. With this migration to alternative battery chemistries from lead acid, you now have nickel-zinc as a choice as well, bringing the immediate power advantages to the market. What you see in the slide here is that the lead acid battery is the CapEx-driven choice. The upfront cost of the lead acid will be lower than the lithium or the nickel-zinc. However, if you look on a total cost of ownership, particularly with the long lives of both lithium and nickel-zinc batteries compared to lead acid, you'll find that the TCO on a long-term basis works out in favor of these alternative chemistries. And that's why there's a migration going on in the marketplace today. There is recognition that this TCO is valid on these alternative chemistries, and they do make sense to bring them into the data center for a variety of reasons. Sustainability is just one of them, particularly around the nickel-zinc battery. So let's talk about sustainability with the nickel-zinc battery. 90% of the battery materials are recyclable. There are no toxic chemicals in the batteries. They can be recycled using existing recycling equipment and processes. So there is a recycling solution for nickel-zinc today available. There's a good recycling solution on lead acid that's been available for a long time. Lithium recycling solutions are still in development. We expect them to prove out over the next few years, but they're in development and less mature than the nickel-zinc or lead acid recycling opportunities. The nickel-zinc battery is also a safe battery, and it has no thermal runaway characteristics. So that means there are no transportation restrictions on it. We routinely ship these batteries in bulk over air, sea, and ground. We also, because of that, can put our batteries into systems, let's say battery cabinets for a data center, like the Wyoming Hyperscale White Box data center, and we can ship those cabinets loaded, fully loaded with the batteries, making the installation a lot easier, whereas lithium has got to separate the batteries from the cabinet at the manufacturing facility, shipped separately, and then be reinstalled on site of the data center, increasing the time and the cost for installing those battery systems. And the nickel-zinc batteries are made with readily available commodity materials, nickel, zinc, copper, all of which are in abundance in the Earth's crust. What we see today as a dynamic in the marketplace for lithium batteries is a tremendous demand, step functions in demand due to the EV revolution that's going on. And a lot of the materials in the supply chain for lithium are going to support that marketplace. And other markets like the data center space do struggle with lead times on lithium batteries because of this demand that's overwhelming in the EV space. The nickel-zinc batteries are not focused on the EV market in terms of being inside the vehicles. The nickel-zinc batteries are an opportunity to work with EV charging systems, but not in the vehicles themselves. So we don't have that vehicle demand. And so our lead times are industry leading for our batteries and solutions. We see lead acid remaining reasonably consistent in their lead times in the market as well. What I'd like to talk about next is how do we measure the sustainability of batteries? And you take the same approach you do to measure the sustainability of all of the components in your data center facility. This methodology comes from the greenhouse gas protocol, and there are levels of analysis that can be implemented: scope 1, scope 2, and scope 3. Scope 1 is your direct emissions from your operations. Scope 2 is the energy used from HVAC or hot water. And once again, when you start looking at the Wyoming Hyperscale White Box design, you realize that the scope 1 and scope 2 emissions is very easy to see the improvements that are made there from the design of that data center. And then there's scope 3. And this is the more difficult one to get your arms around, because it means you need to look down your supply chain and understand how are the emissions at your suppliers and the different components and products that you acquire from your supply chain. And because of that, scope 3 is not as well used in a lot of markets. Many data centers are operating today with solid scope 1 and even scope 2 analyses, but struggle with scope 3. And sometimes that struggle is based on the fact that there is not readily available data for the data center operator to use. And what we'd like to talk about is the availability of data today at the scope 3 level for data center energy storage systems. And I'll take a dive into the analysis that's been done, third-party analysis on this next, all the way down to the scope 3 level. This is a picture from the greenhouse gas protocol. You can go to their website and see how the scopes of emission work. And so what you've got with this analysis methodology is an opportunity to improve your carbon footprint by looking at your scope 1, 2, and 3 emissions. And as I said, our Scope 3 battery data is now available. And so now you can use your batteries in your data center as part of your carbon accounting. And that's not something that's been available for some time. So what does that look like when you evaluate energy storage systems for their carbon footprint or greenhouse gas footprint? There are a variety of environmental key performance indicators that are used. The first is energy intensity. What that's about is, excuse me, what that's about is how much energy does it take to make the battery? And that's all the way from the mining of materials all the way up through the manufacturing process and shipping the batteries. Greenhouse gas intensity, how much greenhouse gas is used, again, from cradle to gate. Gate would be the shipping of the battery. Water footprint, cradle to gate, again, mining all the way up through the shipping. Volatile organic compounds, certainly something we all want to see minimized in manufacturing of any product. Again, cradle to gate. And then finally, carbon return on customer purchase and carbon payback time. So these are, if you evaluate the first four KPIs that I've just talked about, you can then calculate, based on the usage case of the battery, what is the carbon return on customer purchase? So how much CO2e is saved per kilowatt hours installed, and then also a measure of carbon payback time. So as you use the batteries in your usage model, how much time does it take to pay back the carbon that was required to manufacture cradle to gate of the batteries? Now, if you look in the center of the screen, we'll talk about third-party analysis of Scope 3 level emissions of multiple battery chemistries. And what you see in the center is a radar plot that offers all of the KPIs I spoke about on the previous slide, the environmental KPIs. And if you start and go around from 2 o'clock to 8 o'clock, you'll see product greenhouse gas, energy footprint, water footprint, and VOC footprint. These are KPIs that are focused on the manufacturing, the cradle to gate of the batteries. And then you get calculated carbon payback time and carbon return on purchase at 12 o'clock or crop, which are based on how much carbon it took to get those batteries to the data center. And what you see here is 4 different battery chemistries. First, the blue one is the ZincFive nickel-zinc. And by the way, a 0 or center of the radar plot is the worst score for that metric. The best score you can get for that metric is at the outer ring or 10 of the plot. So you can see the ZincFive around the outside of the radar plot for the most part. The lithium-ion is an average of a variety of lithium-ion chemistries, and we'll talk about that in the next few slides, which chemistries were analyzed. Lead acid is also an average of lead acid chemistries. We'll talk about which ones specifically. Is in the yellow, lithium in the gray, and sodium sulfur was included in the analysis by the third party, but they're not that popular in the data center today. And so how do you interpret what you see on this radar plot? The analysis includes a climate impact score, which you see on the upper left corner. And that's the climate impact score for the ZincFive nickel-zinc battery, with a score of 1 being the worst score on climate impact, so having a very high climate impact relative to a chemistry scoring 10, which would be the lowest climate impact. And what you see here is the nickel-zinc battery got a 9.4 out of 10 score on this analysis. So that's what that radar plot results out in when you apply the algorithms to calculating the combination of all these metrics. And then if you look to the far right, the United Nations Sustainable Development Goals are addressed. 4 of the goals are addressed here in this type of analysis. Once again, very applicable to any data center that would like to do Scope 3 analysis. Let's talk about some of these metrics and the scores. And by the way, you can see this report on the ZincFive website. You can go there and download this report from a third-party analysis. This is carbon payback time and carbon return on customer purchase. Let's just look to the right at the charts. You can see starting on the left, we've got lithium-ion NMC, lithium-ion NCA, and lithium-ion LFP. So when we talked about averaging the different lithium chemistries, those are the three that are in the average. And the blue bar is the average value for this metric. The black lines are the range based on how these batteries get manufactured, by whom and where and how. So there can be significant range differences, but the analysis did focus on the average for those chemistries that was found in the marketplace. Moving to the right further is lead acid. There's lead acid AGM, absorbed glass mat batteries, lead acid gel batteries, and lead acid pure lead batteries. So those are the three lead acids in the average and the radar plot on the previous slide. And then finally the sodium sulfur there, and then the ZincFive in the green on the right. So if we look at the carbon payback time, the nickel zinc has a very short carbon payback time because there's a lot less carbon that went into the cradle to gate manufacturing of the product. It typically is around 0.16 to 0.2 years, so less than a year. If you do the math, lithium ion averages about 400% or 4 times longer. Lead acid is about the same, about 400% longer for carbon payback time. If we go to the crop, which is the carbon return on purchase, the nickel zinc crop or return to customers on the purchase is 6 times higher than the lithium ion, particularly the NCAs, and then 4 times higher than the lead acid AGM and PVA batteries. So there's, once again, significant advantages on carbon payback time and carbon return on purchase with the nickel zinc batteries. Let's dive into the other metrics that are measured versus calculated. And these are greenhouse gas emissions measured as CO2 equivalent per kilowatt hour of stored energy. So once again, the data is the same: 3 lithium types, 3 lead acid, sodium sulfur, and ZincFive, nickel zinc on the right. The greenhouse gas footprint is 62% lower with nickel zinc than lithium, and 37% lower than lead acid. And you can start to see why the carbon payback time and the carbon return on purchase is better because of this lower footprint, as an example. Next is energy intensity. So how much energy input was required per kilowatt of stored energy in the battery to manufacture it. And once again, the nickel zinc is 33% less than the lithium average, 23% less than the pure lead, and 12% higher than the AGM and the gel. So the AGM and the gel actually have a smaller energy footprint in this case than the nickel zinc. The water and the VOC footprint. So this is the water used for raw material extraction and manufacturing, and then also volatile organic compounds. These are undesirable compounds used in manufacturing processes. And the ZincFive battery requires 96% less water for material extraction and manufacturing compared to lithium batteries. There's a significant amount of water used in the mining of materials for lithium batteries. And then on VOCs, and you can see that lead acid has very little water extraction as well. It's also quite small. So lithium is the battery that uses the most water in its manufacturing and cradle to gate measures, with lead acid being low and nickel zinc being low. Actually, lead acid would be even lower than the nickel zinc. And then the nickel zinc battery manufacturing requires no VOCs. Neither does the sodium sulfur. There are VOCs used in lithium batteries, and lead acid uses more VOCs than the other chemistries in the analysis. So there's a quick overview of the information around Scope 3 level emissions for different battery chemistries used in the data center today. So that means you can now consider battery inventory in your carbon accounting. You can also start establishing sustainability criteria for battery sourcing, which is exactly what Wyoming Hyperscale White Box did as they looked at their opportunity for energy storage in their data center. And I think the data center industry can challenge the energy storage industry on improving sustainability. Now that we've got this data, how do we make it better? That's really what the customer can say to the energy storage manufacturers. And again, if you're interested in more detail, the full report is available at the ZincFive website.
Thank you, Steve. So to summarize, what we're building at Wyoming Hyperscale is a step change in the carbon footprint for hyperscale facilities. We are drastically reducing the amount of power and water consumed, and thanks to ZincFive, we are drastically reducing the embedded Scope 3 carbon that is being put in our facility as we construct it. So thank you all for watching.
Thank you, Trenton. Just to summarize around the nickel-zinc batteries and their contribution to data center safety and sustainability. The battery technology is safe, no thermal runaway, and that's exhibited in the UL testing for thermal runaway that is done for all battery power solutions that go as stationary energy storage indoors inside buildings. It offers a smaller carbon footprint for equivalent power. So not only is the carbon footprint smaller, but the physical footprint, because of the high power density and the immediate power capability of the nickel-zinc batteries, you can get a smaller physical footprint as well and take up less space in your data center for energy storage and dedicate more of that space to income producing data processing equipment. Batteries are fully recyclable and have a low climate impact versus the other chemistries that are in the market today. So thank you so much for listening to both Trenton and I talk about where we're going in the data center space at both the facility level as well as the energy storage in that facility.
Brilliant. Thank you very much, Steve and Trenton. We'll now move on to the Q&A part of this session. I can see a couple have already come in, but if you haven't already, please do submit your questions and we'll endeavour to get through all of them in the time we have left. So the first question which has come up is what part of the data centre is having the biggest sustainability impact? I guess that's the question for you, Trenton.
Yes, so it's mainly just moving from air-cooled to liquid. As I mentioned earlier, it allows us to increase the density more than 10x over air-cooled data centers, and that drops the amount of space that we need on the data center floor by 85 to 95%. So that's the biggest savings.
Fantastic. And another question, I think this one will probably be for you, Steve. How can data center operators incorporate batteries as an asset into their carbon accounting?
Yes, it's a great question, because until recently, there really hasn't been any data to enable anyone in the data center trying to do their carbon accounting work to include the battery energy storage. And there is significant energy storage in a lot of data centers today. So with the new data that's available, and it will be continuously updated in the future, the data center operator can now get this data and start using it for their Scope 3 analysis level and understand what the energy storage contribution is to that.
Okay, fantastic. And another question has just come in. What are the opportunities for heat capture and reuse in a data center? Trenton, is this one for you?
Yes, so this is the subject of another group that has been formed within the Open Compute Project, OCP, around heat reuse. So the first one that we're after is indoor farming. There's also district heating. We're also evaluating newer technologies in direct carbon capture and plastics recycling. So some of those will require us to high grade the heat a little bit, but starting with a good amount of hot water is beneficial for a lot of different processes.
Fantastic. And we are running a bit low on time. We have had another question come in. How is nickel zinc compared to alternative batteries in terms of recycling? Steve?
Yes, so the recycling story there is lead acid has a very good recycling model in the marketplace today. Customers can get core credits for their lead acid batteries when they recycle them. I think and it's somewhere in the 99+% recycling rate in developed countries. So it's one of the best products, best ratings for products being recycled.